Hello there, calculus folks. This lesson is on derivatives of log functions. And here's the warm-up, and off we go. If you haven't done it, pause and do, because here we go taking it up. Remember that to calculate log base something that's not 10, that we do a change of base formula. So log of the top over the log of the bottom. And in fact, now that we know a different base, we know this uh, natural log base, the ln, we could use the ln of 18 over the ln of 2. In fact, the change of base works for any old any old base. I could take log base a of 18 over the log base a of 2. They're all the same. Change of base, it doesn't matter what base. And so, I mean, you'll find out in university more and more, especially if you're taking math courses rather than science courses, that you're going to use the, well, it depends on what science course as well, I guess, um, that you're going to be using the natural log base rather than base 10, just because it's so much more useful and common. So what are we up to here? Well, we want to write that as a log function base e. Well, why would we do that? Because we know what the derivative of the natural log is, right? And we'll prove that today, but we did that in the investigations earlier on. Well, this is just the change of base, right? Log of the top over log of the bottom, or if I want to use base e, ln of the top over ln of the base. If I wanted to write that as like a stretch factor, if I want, yeah, I can. It's still just um, a log base e in this case. And remember, what the derivative was 1 over x, which was pretty impressive and neat, but we haven't really proven it. We did some investigations, but we haven't really proven it, and that's what's going on first off here. So we want to find the derivatives of ln and the derivatives of any old log base. So earlier in the investigations, we know this is true. So again, that's a fact we know. When we want to take the derivative of ln, it's 1 over ln of x is 1 over x. So let's prove it. Well, how do we prove a derivative? We go from first principles. And we're going to do that almost straight off here. We've got f prime at x then is equal to the limit. Do you remember this? I hope you do. F at x plus h minus f at x, and this is true for any old function. But in this case, I have got f at x is ln x. So f at x plus h is ln of x plus h, right? So, okay, let's put that in there and see if we can think about what to do. When we were doing the exponential function the other day, we could factor out, but we can't do that, right? We can't just factor out a ln x. It doesn't work the same. But you might be thinking, well, maybe there's one of the log rules I can use. Yeah, remember, the log of something minus the log of something else, when it's subtracting on the outside, it's dividing on the inside. And how is that going to help? Well, we'll see. We'll see soon. This is actually a pretty nasty development. One that you wouldn't necessarily be asked to come up with on a test, but certainly it's going to make you a better person by watching and understanding here. All right, so I'm going to put those two together, but notice that I'm going to have ln of a fraction. So I want to get rid of this over h thing. So I'm just going to move it out of the way and write it as 1 over h like that. I hope that doesn't scare anybody. And then I'm going to write the ln on the inside. You see, I've just used that logarithm rule, right? And ln is just a logarithm base e. Okay, so now what am I going to do? Well, I'm going to simplify this a little bit. I'm going to write this as ln of 1 plus x over h. The problem is I don't really like this h over x business. It doesn't look very familiar to me at all. So I am going to change something. I'm going to make t be h over x. Okay? Why t? Well, just a variable I picked. So where this was, I'm going to put t there. Everything else is going to be the same, I suppose. But notice that anywhere that I had an h, I'm going to have to fiddle around with it, because now if I've got t as my variable, I need t's to be everywhere, not just in that one spot. So this 1 over h, I've got to rearrange this so I can substitute for 1 over h. Well, how do I do that? I'm going to rearrange this little formula here, so that's tx is equal to h. So there, okay, so this business is going to be 1 over tx instead of 1 over h. All right, fine. My index of the limit here was an h as well. Notice as h goes to 0, what happens to t? Well, t goes to 0 as well. So no problem. That doesn't change much at all there. Well, maybe I'll put that in blue this step, just so we can see that we did substitute that. When h goes to 0, t also goes to 0. Okay. I'm still having trouble evaluating. If I put t equals 0, I still get 0 over 0, and it's still no good. But I have to keep fiddling. What I'm going to do is I'm going to split this up. You see this here? This x has got nothing to do with the rest of the limits. And we've had this trick before where the x part, which is really where our derivative is going to come from, there's my 1 over x right there. You see that? Oops. 1 over x. And what I'm going to do in a step is I'm going to pull this out front, right? Because it's got nothing to do with t, it's kind of like a constant. Well, it's a function, but nothing's changing as t goes to 0. And then now I'm left with this. All right. And there's going to be some shenanigans mathematically here in a second. But let me just sort of make you think about this. Since this is 1 over x, and we know if f at x is ln x, we know f prime at x is 1 over x. So what does this limit have to be? Well, this has to be 1 somehow. Now we just have to work for it to happen. And I know you could put in values of t that are close to 0 and work it out, but I want to use a bit of a calculus-y sort of thing. I'm going to use a log rule in here, and this 1 over t I'm going to put up there. One over t. And that's the exponent. I want to put that a little bit closer so it doesn't look goofy. 1 over t. Okay, this is starting to look familiar. I have 1 plus t to the exponent t, and in here I have the limit that t goes to 0, 1 over t. This is something we've seen earlier. Do you remember what this is? This is equal to e. This was one of our definitions of e. This was essentially the bank and the interest question. This is e. All we have to do is sort of, can we pop this lawn out of the way? Well, yeah, we can actually, and it's all got to do with the limit rules. If you remember back to, this is chapter 1 stuff, the limit rules. I said the limit of a sum is the sum of the limit. So we could just split up the two functions. And we actually saw that if it was a power, the limit of a power is the power of the limit, and the exponent can go on the outside. So is it okay for me to say the limit of a ln is the ln of the limits? And indeed it is. Basically, the idea is, as long as there's no shenanigans, there's no funny business going on for these functions, that they're continuous, as long as they're continuous, then I can do this sort of thing. And this is true. This is continuous here. So what can I say here? I can say that the limit of a ln is the ln of the limit. And what's this? This is e. What's the ln of e? Well, it's a function composed with its inverse. Pretty cool derivative. Therefore, f prime at x is equal to 1 over x. And there's a pretty fancy first principles proof, one that you wouldn't be responsible for. Kind of like an easier version to convince yourself of that the derivative is 1 over x is if we said here like this, and then rearrange this version, basically exponential function of both sides. So then I have a different form of y equals ln x. I have e to the y equals function composed with its inverse. Now take the derivative. If I take the derivative of this, the right with respect to x, then the right side is 1. The left side, well, what's the derivative of e to the exponent y? Well, it's just e to the exponent y, but this is a chain rule, so I got to take the derivative of the inside thing. I get y prime equals 1 over e to the y. But what's e to the y? E to the y is x. And there's kind of a cheapo fast proof of that. Okay, well, with all that said, now we've hopefully convinced you that this is the case. If f at x is ln x, that the derivative is 1 over x. Now we've got other business to get through, like getting some examples under our belt so we can do some homework questions. But first, what about the general log function? Log base anything. How do I find the derivative of log base anything? Well, the idea is now we can lean back on our old like on this fact. If we can somehow lean on, if y equals ln x, that y prime is 1 over x. If we can somehow use this, then we're golden. And it goes back to our warm-up question. Log base b of x is the ln of x over the ln of b, isn't it? So now take the derivative of this. Well, notice that this is just, the ln of b is just a number. B is a number like base 2 or base 5 or base 10 or whatever. So I could think of this as a number out front, and then there's the function. So the number, when I take the derivative here, this is going to be y prime. It just hangs out front, right? The derivative, that hangs out front. What's the derivative of ln x? 1 over x. So then the derivative is 1 over x ln x, or ln b, not ln x, ln b. So therefore, here's another rule to get into your brain. If we have y equals log base b of x, then its derivative is 1 over x ln b. Not ln 2, ln b. And this is a number. Sometimes you'll write it in front of the x, sometimes behind the x. That doesn't matter. Okay. Remember that we also saw in the last couple of days that if we had the exponential function and we took the derivative, that was just the function itself times ln b. Well, there's a symmetry here, isn't there? There's the derivative of the original function, and there's kind of like the fudge factor that makes up for that. It's not the natural log base. So These are now in your brain, correct? All right. Well, we'll pick up the examples in part 2.